Hello, good evening. Can you hear me?
Yes, sir. Good evening.
Yeah, how are you?
I'm fine, sir. How about you?
Yeah, Alhamdulillah, everything is good from my side. Yeah.
Yes, yes.
Okay, so basically today discuss about the some advanced topic on remote sensing for soil and water management. Okay, such as soil pH, as well as discuss about that soil moisture using multi satellite imagery, such as Landsat or
Yes.
Sentinel. This type of multispectral remote sensing, how we can use and make the soil moisture. Also, we talk about that crop water stress monitoring. So let's wait to discuss about all of those step by step. So let me share my screen. Yeah, can you see my screen? Is it visible?
Not yet coming.
Okay, so now it's okay. Huh?
Yes, now it's coming.
Okay, so let's go start. Okay, so previous class I discussed about this type of topic. Some topic is not completed, such as crop stress monitoring, or also soil moisture, and also soil pH. Okay. So first of all, I discuss about that soil moisture. Okay. So we already know about the some data set. Okay, but this type of data have a problem because this type of data is not the good resolution. Okay, we find out that soil moisture from SMAP. So this type of data is very pixel size is very high, okay, 9,000 meter. So that's the region we need to apply the different types of model in remote sensing. So one model is called that this model. This is the optical trapezoid model. So it's very popular model to identify soil moisture. So this is the new variant of the optical trapezoid model of remote sensing for soil moisture and water bodies. So in this paper, they are mainly explain about this method, how they create this type of model. So optical trapezoid model. So this type of model we try to implement using remote sensing, and further we can easily monitor the soil moisture. Okay, because it's very high resolution than others, Landsat or Sentinel when you apply. Then we can easily use the OPTRAM model. OPTRAM basically is short form. It's the optical trapezoid model. This is the full form, optical trapezoid model. So this model we can easily use, and further we can easily compute the soil moisture. Okay, so let's go. I will try to explain all of those things. You can get the idea. So in this model, we find out that this is the chart about the optical trapezoid model. So in the chart, if you check this the X column, we find out the NDVI, and Y column we find out the STR. STR basically it's a short wave infrared reflectance. Okay, so this is the STR. We find out that, and we can get that these two things. Okay, let me open the code editor. Then it will be more better. So this model basically it's different.
Sir,
Yeah, please.
sir, can you please remove that
Uh,
smaller pop-up
yeah.
window? Yes.
So
Yes.
first of all, this model we find out that NDVI. Okay, NDVI basically normalized difference vegetation index, measure the vegetation density and health. So this is the one factor for this model. Okay, it's measurement the vegetation density as well as and health. Okay, vegetation health we can easily identify using the NDVI. Another is that it's called the SWIR. So this is the another factor. So this is the short wave infrared reflectance. Okay, this short wave infrared reflectance it's sensitive to the soil moisture. Okay, so it's sensitive for to soil moisture, to soil moisture. Okay. So this is the short wave infrared band is soil moisture because water body absorb the strongly. Okay, water body water body water body water body strongly absorb in the SWIR or short wave infrared region. Okay, because it's strongly absorbed, so that's why soil moisture is very sensitive for this band SWIR. Okay, and when you plot NDVI versus SWIR reflectance for all pixel, then we find out this type of trapezoid model. Okay, so this is the STR, okay, short wave infrared reflectance. Another is the NDVI. So when you plot, okay, all pixel in an image, we find out the trapezoid shape. And this trapezoid shape, we find out this type of things. First one, it's called that your top left corner. Okay, top left corner. Okay, left corner. So basically it's the trapezoid shape, and in this trapezoid shape we find out the top left corner. In the top left corner, it's called the dry bare soil. Okay, in the top left corner. Okay, dry bare soil. And the top right corner, we find out wet bare soil. Then bottom left, we find out that dry vegetation. And finally bottom right, we find out wet and dense vegetation. Okay, so this is the so basically when this we find out the trapezoid shape. So when you plot, suppose when you plot NDVI versus SWIR, when you plot, then we find out the trapezoid shape. Trapezoid shape. Okay, in this shape, in the top left corner, we find out the dry bare soil, because in this time, in the top bare soil, we find out that high short wave infrared and low NDVI. Okay, so in this region, in the top left corner, we find out that high SWIR value and low NDVI value. So that's why it's called the dry bare soil. Okay, and then second, in the top right corner, it's called the wet bare soil, because in this time we find out that low SWIR and also low NDVI. So in this zone, in the top right corner, it called the wet bare soil, because we find out the low SWIR and low NDVI. Okay, it's the wet bare soil. And finally, another, in the bottom left, we found out dry vegetation, because in this region we find out that your NDVI is very high. Okay, we find out the NDVI is very high. So high NDVI. Okay, and dense vegetation, it's also high NDVI. We find out it's a high NDVI.
And so, sir, the high NDVI, it means the short wave infrared will be low, is it?
Yes. Because SWIR indicating about the water. Okay, you can say already say about the water
Yes.
body is they strongly absorb this band. Okay, so
Yeah.
suppose I find out the vegetation this type of place, but then we find out the low SWIR. Okay, we find out the some water basically in the all of trees have some small water, so but it not miss high. Okay, low SWIR find out in here. The same for the bottom right. So in this paper you can see also find out this type of shape. You can see the we find out that the top left corner, okay, then also find out that top right corner, bottom left, and also bottom right. So the position of each pixel inside the trapezoid reflect, and it's called the soil moisture condition. Okay, inside in the trapezoid reflect. Okay, so in this portion we find out that it's a soil moisture. We find out in inside on the trapezoid all of pixel indicating about that. Okay, so now you can see they are also calculated this type of formula. You can see STIR. So in this formula, dry and wet edge can be determined. You can see we find out the dry edge and wet edge. So now why a trapezoid? Well, two main regions because vegetation and soil moisture. So why a trapezoid? Why it show the trapezoid this type of model? So I'll go explain about that. Suppose. So why a trapezoid? So first of all, vegetation. Vegetation. So NDVI increase with dense vegetation. Okay. So NDVI, this NDVI increased with vegetation density. Okay. Suppose if the NDVI is high dense vegetation, it's increase the NDVI value. And vegetation marks soil reflectance. Okay. And vegetation marks soil reflectance. And finally another one is that soil moisture. So in this case what happened, a SWIR, this band reflectance decrease as soil moisture increases increases because, okay, so I'll suppose soil moisture increases because we find out that water absorbs SWIR radiation. Okay, so this is the region. So as NDVI increase, suppose as NDVI increase, both dry and wet soil show lower SWIR reflectance. Suppose some place NDVI is very high, then both dry and wet soil show the lower SWIR reflectance, but the gap between dry and wet is narrow and forming a trapezoid rather than a simple triangle. Okay, so now suppose NDVI is increased or more vegetation, then we find out the both dry or wet soil, both of soil. If the NDVI increase, we find out the lower SWIR reflectance. Okay, but the gap between dry and wet is narrow and forming a this type of trapezoid model. Okay, this type of trapezoid model forming. So that's the region we find out. It's a this type of shape. But now we discuss about the what is the driest one, what is the wettest. So let's go. So this is the component of this model. Components. So in this model, components, first components we already know it's a dry edge. Basically this one dry edge, and you can see this is the wet edge. We find a dry edge and wet edge. These are two, as well as pixel position. Okay, so we try to use that. What is the dry edge? Dry edge, it's the upper boundary of the trapezoid and represent the maximum reflectance of SWIR bands for each NDVI level. So I also write it, suppose it's indicating about that upper boundary of trapezoid, upper boundary of the trapezoid, and it represents maximum SWIR reflectance, okay, for is NDVI level. Okay, it show the maximum reflectance, that is the driest. Okay, so physically we find out it's in the bare or dry soil, or it was stressed vegetation. Okay, we find out the driest region. And then what is the weight is? This weight is lower boundary of the trapezoid, lower boundary of trapezoid, and it represent the minimum. Okay, it represent the minimum SWIR reflectance, for is NDVI levels. This is the weightage and price. And finally, pixel position. This is the another component. So this is the third component. It's called the pixel position. So in the pixel position, what happened? Any pixel in the trapezoid lies between dry and wet edge. Okay, so and its relative distance from the driest tell us how wet to dry is it. We can find out from here. Okay. So first of all, let's go. I show a practical example. Then you can get the idea how we can work with the soil moisture using this model. Okay, so first of all, we try to import our study area. So which area you want to monitor? So let's go. Just simply import the study area. Any cropland, anything you can simply do. So let me just try to make this model for this study area. So this is my study. I simply draw a study area line. So this is my study area. Okay, and I put the name as a RY. So for this area, I want to monitor the soil moisture using the OPTRAM model. Okay, so optical trapezoid model. So now I want to use, suppose, Landsat imagery. Just I simply upload. Just simply get to the browse data catalog, and then I want to just work with the Landsat. Click on the Landsat, and I want to work with, suppose, Landsat 8, and then I just choose the surface reflectance. Okay, then simply copy this snippet ID. And take a variable, suppose Landsat 8, and equal, and paste. So now simply filtering this image collection, we already know about that. So just filter bounds with our study area, which is RY, then put the filter date. So I put the date year of 2024 1st January, from year of 2025, suppose January 1st January. Okay, so I take the 1 year 2024. Okay, so just I put this type of time period, and after that just simply filter the cloud cover. So I put here the filter, then put here earth engine dot filter dot, suppose, less than I choose cloud cover less than suppose 1. So now let's check how many images are available. So print the Landsat 8 and use the size function. So now computing how many images are available for my study area. We find out only for the 6 images. Okay, we try to use it all of images. So now this image we find out, and this image we need to use. First of all, we need to reproject the scale value. If you check, this image have this type of things. You can check. We find out this type of scale value and also find out the offset value. So now we simply multiply all of images and also add all of offset value to convert the your surface reflectance value. Okay, so for that we try to create a function. Okay, just we create a function. So in this case I just use I take another variable. Suppose I create a function. So I put a variable name, suppose scaled LST or scaled L8. Okay, so now I just create a function. So create a function, I put the element name, suppose img, and put my argument. So what is my argument? My argument is that all of image I just simply multiply with this scale value and also offset value. This is my argument. So for that, take a variable. Suppose I put the variable name is that sr equal, and then I call the element name img. This element I want to multiply with this scale. So my scale is that 0 on this scale. Just like copy and use it, and also add the offset value. This is the offset value, negative 0.2. This is my offset value. Just like copy and paste. Okay, so we find out simply reflects this type of things. And not only for that, I also select the image band. So you can say I want to select all of bands. Suppose SRB1 to SRB7. So all of bands I want to select. So for selecting all of bands, just apply another function dot select and select SR dot and also put the this. Okay, star. Yeah, it star means that all of we just consider. And if you want, you can also put at the SR, suppose SRB. So then what happened? Then SRB, you can see SRB1, SRB2. So you can see this. Just I simply mention this SRB and underscore. And when I put the star, it including all of bands SRB1 to SRB7 because it is same sequence. We find out. Okay, just I put this type of bands and also multiply and also add. So now these two parameter I compute in here. So I want to compute NDVI using this all of bands for all of images. Okay, so for that I create this function. So I need to compute the NDVI as well as also compute the your brightness temperature. Okay, or LST or brightness temperature we compute it. So for that, just take a variable, suppose NDVI, and I just call the SR. Okay, just I copy the SR because this it is stored all of image, multiply and also addition with my scale factor, and I want to compute suppose NDVI. So just apply normalized difference. Normalized difference I apply between two band SR B4 5 near infrared and SR B4. Just we simply define and I rename it dot rename as a NDVI. We put the name as a NDVI. Okay. So as well as you also compute the your brightness temperature. So for that, just take a variable. I put the variable name suppose LST, and I have to compute using this image. So just I call the element name. Okay. And in this element, from this element, I select the brightness temperature band. If you check brightness temperature band, we find out in here STB10. Okay, this is the brightness temperature band, and this is the scale value and offset value. Okay, we also need to use it. So just I paste here, and then apply multiply function. Multiply this scale value and also add the offset value. Okay, this is the offset value. 149. Just I copy and paste. So we compute it and also rename it. Suppose I just I put the dot rename as a LST. Okay. So we compute the NDVI and also compute the brightness temperature using all of images. Okay, just create a function. So after creating this function, what I return, so we need to combine the LST and NDVI. These two band we simply combine. So for that, I simply mention in here return. So I want to return and I want to combine. So put here ee dot image dot cat function to combine between NDVI and also LST. So simply combine, and then we simply copy. Yeah.
What if I write return maybe img.add bands, then I mention those NDVI and LST. Will it function?
Okay, so in this case, we try to combine NDVI and LST. We are just make combine the two band, just simply and just make the single, store it in a single variable. Okay, NDVI and LST. So further, we simply compute NDVI and LST, and then we return this image.cat. These two things we simply add. Okay, combine these two things using the e.image.cat. After that, we simply copy these properties and apply all of images. So put here the copy properties from element and apply all of. So put here the img dot property names. So just we copy the all of property names. So now this is our function we computed. This function we need to connect with our collection. So what is my collection? This is my collection we already compute. So for connecting, just use here the map function, just paste and apply the dot map function, bracket start, and also close the bracket. So now if you check, just print and check what happened. Just print and call the scaled LX. So this is my, and run the code. So now you find out this type of total 6 images, and if you check the all of images, just click on here and check the bands. We find out the only for the two band, NDVI and LST. You find out again. So just to simply combine the two bands together, NDVI and LST. For each images, total 6 images I have for my study area less than 1%. So just I simply find out the two bands, NDVI and LST. 6 images. Okay, you can see we find out only for the two bands, NDVI and LST. So now these things we need to, from this NDVI, we just choose only for high NDVI values. Okay, suppose high NDVI values we simply choose. Suppose greater than 0.4 or 0.3. Okay, this type of NDVI we simply choose. And this thing we simply update marks with our LST value. Okay, so basically find out the LST full cover area and also LST bare land area. Okay, suppose for the LST, when you identify for the vegetation, so suppose we need to create a threshold value. Suppose I choose greater than 0.4 and take all of pixel of NDVI and then marks with my LST layer. When I take the bare land, so how I can define the bare land? Suppose we choose NDVI less than 0.2 or greater than equal 0 and less than 0.2 or lower value of NDVI we simply consider. So let's go and try to do it. So just take a variable. Suppose I put the variable name LST. Suppose high NDVI. You can put any name equal. So now create a function. So I put the function keyword. I put the element, suppose img. So So in this time, what is my argument? My argument is that I just select high NDVI value. Okay, so for that, take a variable, suppose NDVI high equal, then call the image and select the band. My band name is NDVI. This is the band name NDVI, and I choose suppose greater than 0.3. Okay, and then this thing simply update max with the condition of LST. Okay, so for that, take a variable. Suppose I put the variable name is that LST. Suppose I LST high I put, and call the image and choose select the band of LST, and this thing simply update max with this variable NDVI high. Just copy and paste here. Okay, and now what I return, so from here I just return this LST high. Just I copy and paste here, and then simply copy of properties for all. Just put here the copy properties all of images same, and also provide the property name. So just put here the image dot property names. Okay, just we simply define. And now these things we simply connect with our collection, NDVI collection and LST connection. We already combined, and it is stored in this variable scale L8. Just a copy and connecting. Just paste here and use the map function and so close. Okay, so now we create this function, and if you print, suppose just print an LST high NDVI, just show the result. Just copy and paste and run the code. So first time we simply find out that NDVI for the higher LST for the high NDVI range. Okay, we find out this image collection. Okay, we find out. Okay, this image collection is stored the LST for higher NDVI. Okay, high value of NDVI. So now we try to identify another one. It's called that suppose low NDVI value, which is indicating about the barren land. Okay, which is indicating about the barren land. So now we simply take that same code we try to use in here, but in this case we simply put the range only for the low value of NDVI. Okay, then others are the same. We try to apply the same, and it's called the NDVI barren land. We try to identify for barren land max with the LST. Okay, so for that, just I copy the same code and paste. So now I put suppose LST in the low. Suppose I change the variable name. I put it's a suppose low NDVI. Okay, and I want to identify low NDVI. How I can identify using the low NDVI?
Maybe less than.
Yes. So suppose I put
0.2
and not for the water. Okay. So in this time we take the range 0 to 0.2. Suppose 0 to 0.2. This range we take, not for the less than 0. So let's we try to put here. So I put here NDVI suppose greater than equal 0 and image dot select the band of NDVI, and it's less than 0.2. So I put this range. Okay, and I put the LST low NDVI value. Others you can also put the, suppose I put it's a LST anything you can put, suppose LST low, or you can put here the NDVI low. Okay, it doesn't matter. So I put the NDVI low, and further these things I just apply update marks using this variable. Just paste here, and also I return the LST low. Just I copy and paste here. Okay, and others keep the same. There is no problem. Okay, I already connecting. Okay, so now if you check, we'll find out another image collection, for LST low NDVI range, which is indicating about the barren land. Okay, so it's indicating about the barren land zone. I also comment, suppose it's indicating about that barren land zone. Okay, zone, and it's indicating about that high or dense vegetation zones, dense vegetation zone. So then we can easily get. Okay, so we find out this type of things. So after computing this type of high NDVI zone or barren land zone, so then we compute some factor. Okay, so in this factor, so let's go try to explain this factor. So this is the first step to compute the your parameter. Okay, this will take me one paper. Just a minute. Just I simply search. Okay, this you can see. You can also do the R package also. Okay, R package basically OPTRAM. So this is the package name. In the R package, we can easily compute this type of model because it's one kind of package. Okay, so this is the package about the optical trapezoid model, and this model drives the soil moisture based on the linear relationship between the vegetation index, NDVI, and short wave WN. So we can also apply. You can see this is the package of R. So then we simply input this type of thing. It also possible to use very easily. Okay, so then very short time we can easily compute. Okay, just simply import the Sentinel-2 image. From the Sentinel-2 image, we need to prepare the NDVI and STR. Okay, and then this library automatically perform the analysis about the your okay, you can see that also put some example about that. Okay, so this is the library. Okay, this library simply connect with our model, then it will also work for that optical trapezoid model. So now we compute the two things. If you check in here, we compute that barren land LST and also compute suppose dense vegetation LST. So after that, it's neat because you are building the temperature vegetation features space, and full vegetation basically it defines the vegetation edge. Okay, suppose these things it's indicating about the vegetation edge. So I'll also write the comment. It's indicating about that vegetation is okay, and the barren land define the soil is or hotter. Okay, so it's indicating about that another is which is indicating about the soil is okay. And further we simply extract the thermal extreme or edge anchor across the period. So first of all, if you okay, so I'll show the term about that. So first one, it's called that we can say that VW. Okay, so what is the VW? VW, it's indicating about the maximum LST found. Okay, it's a maximum LST found. Okay, and suppose like that, it's a maximum LST found. Okay, it's a maximum LST found or compute the sorry, VW is not maximum, it's a minimum. Sorry, it's a minimum. Okay, VW is the minimum LST found. And what is the VD? VD basically is the another term. So it's called the maximum LST found. So it's a maximum LST found. Okay. So VW and VD for vegetation pixel. So we can use it two argument or two factor for vegetation. for vegetation. For vegetation pixels, we are use this. Okay, so VW and VD. What is the VW? Makes minimum LST found region, and this region we find out in that coolest. Okay, it's called the coolest. Coolest mainly. We can also say that it's a wettest vegetation, not dry vegetation. Wettest vegetation. Okay, and maximum LST found. It's mainly warmest or hot vegetation, or we can also say that warmest, or you can also say it's a driest vegetation, okay. So in the vegetation pixel, basically from this from this or dense vegetation zone, so from that we need to compute the two things, VW and VD. And what is the VW basically minimum LST found region. It is the coolest or wettest vegetation, and VD is the maximum LST found. It's called the warmest or driest vegetation. Okay. Same as we find out also another things. It's called the for barren land. So for barren land pixels, we find out the two another factor. One is that it's called the IW. What is the IW? IW basically it's the minimum LST, and another thing is that ID. Okay, ID is that maximum LST. So two factor with IW and ID. So what is where we find out the IW? IW basically it's called the coolest bare soil. Okay, coolest bare soil. It's called the coolest bare soil. And we also say that it's a relatively wet soil. Okay, so it's minimum LST, it's indicating. And same is the vice versa. It's called the hottest bare soil. Hottest bare soil. Okay, and it's a called the driest soil. Okay. So we find out the VW and VD. Okay. So now we try to compute the VD, this type of factor. Suppose VW, then VD, then IW, ID. So let's go try to compute. So for that, take a variable. I put the variable name, suppose VW equal, and I need to compute it for LST, basically our vegetation pixel. Okay, VW, this thing we compute from the vegetation pixel. Okay, from here. So just I copy and compute the minimum LST from here and paste here. Okay, I want to compute the minimum, so I put here the LST dot mean. Okay, and I have to compute the value, put here the reduce region, this function to compute the value, and then define the value. Suppose reducer, I want to compute the minimum value, so put here ee dot reducer dot mean, I compute, and then I need to define the geometry. So geometry basically it's come ROI, shapefile variable name. Finally scale, we put the scale 30 meter for Landsat. Okay, and then it's option. Then I want to extract the values, so put here the dot values, and also put here the get 0. Okay, mainly extract the values of BW, and its work as a number. So I define the ee dot number. Okay, define the number. So now we try to print and check the result. What happened? Suppose BW, run the code. Oh my god. Okay, so
Yeah.
okay, so here we face a problem. So this, okay, we need to close the bracket in here and also remove the one parenthesis. So now run the code.
Yeah. Yes.
So we find out this type of value. Okay, so it shows the result as a Kelvin. Okay, we compute the Kelvin. It's not, doesn't matter. Kelvin or degree Celsius, we can easily convert. So I keep the Kelvin, no problem. So we find out this is the minimum LST found. We find out this is the, and it's a wettest vegetation or coolest vegetation. We find out this VW, and same for the VD, same process for the VD. Just I copy the code, just I copy and paste here. Okay, I put it's a VD, and I compute from the vegetation pixel. I compute that maximum, so put here the max. Reducer, I want to compute the maximum value, I want to compute, so put here the max. And for the same, I want to just copy and paste and run the code. So now you find out the result for your maximum. We find out this type of Kelvin. Okay, this is the maximum, this is the minimum, and it's called the we find out it's a maximum LST found or driest vegetation. We find out this type of value, and this is the wettest vegetation, IW. Okay, so I hope you can get that. So now another, so we try to compute for IW and also ID. IW, minimum LST, coolest bare soil, for the barren land pixel. Okay, so this IW and ID we need to compute for the barren land pixel. We already defined the barren land using this way. Okay, so this variable is stored. So for that, just I copy the same line of code because it's the same. Just I copy and paste. So now define the barren land pixel. Barren land pixel is stored in this variable LST low NDVI. Just I copy. This is the barren land zone, and I just define in here. I put it's a IW is indicating about the minimum. Okay, all of those are same. I also print here the IW. Okay, so then others keep the same. So now for that we need to compute the ID. Same process, just I copy and paste, and I define it's a ID. So in the ID section, so same LST low NDVI, and I put here the max because I need to compute the maximum LST or hottest barren land or hottest bare soil for the driest soil. So put here the max, and also put here that max, and RY I call the ID. So now we can easily get this two value. Okay, for the IW and ID we find out this type of value. So now here we find out the mean and max first collection per pixel we compute. Okay, okay, so now we interpretation. So here VW. Okay, so I'll write it. Suppose in this case VW and also VD. So these two things, it's indicating about the vegetation is. Okay, vegetation is, and the vegetation is extreme over the season. And also what is the ID and IW? It's indicating about the soil or bare soil or bare is extreme over the season. Okay, so now after that we need to compute another things. It's called the SD and SW. Okay, so it's called the S spans. So let's go try to discuss about that. What is the S spans? So S span. In the S span, basically it's quantify how far soil and vegetation thermal stress are apart at the two moisture extreme used to parameters trapezoid or triangle geometry, but trapezoid. So in this case, S span, it can be we can get the two things. One is the SD, another is that SW. So we define the S span, SD and SW. And what is the SD? SD equal, we can write ID minus or VD. Okay, and it's indicating the temperature span. Temperature temperature span between driest bare and driest vegetation. Driest vegetation. Okay, it's indicating about that span, or suppose soil and vegetation gap on the dry side. Soil or vegetation gap. It indicating about the soil and vegetation gap. Okay, I'll write it. So short form, it's called the soil and and vegetation gap. Soil and vegetation gap on the dry side. On the dry side. Okay. And what is the SW? SW, it's indicating about the IW minus VW, and it's indicating about the temperature span between wet bare and wet vegetation. Okay, so temperature span between two. One is the wet bare and wet vegetation. Okay, or soil and vegetation gap on the wet side. Yes, simply you can say that soil and vegetation gap on the wet side. So this is the age span. Age span, basically it's quantify how far soil and vegetation thermal stress or effort at the two moisture extreme. So now we try to compute this thing. So it's very easy. Just take a variable. Suppose SD equal, I call the ID dot subtract with BD. Okay. Then take another variable. Suppose SW, and what is the SW? IW. This thing subtract with VW. Okay, so we compute the age spans. Okay, SD and SW. SD, basically its temperature span between driest bare and driest vegetation, and SW, its temperature span between wet bare and wet vegetation. Okay, so now we just apply a formula. So this formula called the soil moisture estimation, and it's called the OPTRAM style formula. So just we simply define this formula, then we can easily compute the soil moisture. But when you compute the soil moisture, we need to create this type of factor. You can see VW, okay, VW, VD. Okay, we need the VW and VD for the your vegetation area. Then we need to compute the IW and ID for that bare land area. After that, we compute the vegetation is span, so for the SD and SW. So now we finally compute a formula. This formula, I write the formula. So this formula, suppose soil moisture equal, we put the formula is that ID plus SD multiply with NDVI minus LST. Then these things we need to divide, just divide with ID minus IW plus,
Sir,
yes, SD minus SW, and we can get the lot of scientific paper. They also use this type of formula.
Sir.
Please.
Hello, sir.
Yes, please.
Sir.
Yeah, can you hear me?
Sir, I don't get you. Maybe the internet issue on your side.
Okay, just a minute. Refreshed myself. Just a minute. I just refreshed. Okay, can you hear me now? Hello.
Yes, now I can hear you.
Okay, so let me share my screen. Okay. Okay, so now we just compute this formula. This is the soil moisture formula, and in this formula, okay, so this is the formula. Okay, so this is the final formula for the soil moisture. ID plus SD, okay, NDVI minus LST divided by. So this formula, when you compute, then we can easily compute the soil moisture. So let's go try to compute this formula. And we are using this formula using our basically this one. Okay, so we just combine, you can see we combine the NDVI and LST, so we need to use this one. Okay, where we combine these two things, we need to use this because NDVI LST is available in here. Okay, just we need to use it and compute this equation. So take a variable, I put the variable name, suppose sm equal, and then paste here. Okay, and we create a function. Okay, suppose just put here function, and put the map function and put the function. Okay, because this function I simply connect with my image collection where I including NDVI and LST, and I put the element name, suppose img, and now put my argument. So my argument is that I want to compute the soil moisture. So take a variable, suppose I put the variable name is soil moist. You can put any variable name, and then call the element and apply here expression, and this is my expression. Okay, so we just close the bracket also. No. Okay, just okay. So now this is my equation. Just I copy. Okay, just I copy, and I just paste. Okay, so this is my equation. I simply paste in here. So now I define what is that, all of those one by one. So first of all, in this case, we find out what is the ID. So ID, it's come from ID. We already compute the ID. You can see we already compute the ID. Okay, so it's come from the ID. Then what is that? Your SD. So I put here the SD. It also come from the SD. Okay. Then what is the NDVI? So I put here the NDVI. This NDVI, it's it also this image. Select the band of NDVI. I already compute the band of NDVI. So put here the NDVI. Then what is the LST? LST. So it also come from this image and select the band of LST. Okay, just we simply define LST, as well as what is the IW. We already compute the IW. So put here that IW, and just put here the IW because I already compute this value. Okay, then what is that? Okay, IW, and others not need, and I just rename it. Suppose I put here the dot rename. I put the rename as a SM or soil moisture. So now I compute this formula, and what I return. So I want to apply this equation all of images. I have total 6 images. I already checked in my collection. So I want to apply it for all of images. So put here return this soil moisture. These things I want to apply for all of images. So for that, just apply the dot copy properties, all of images. So img, and also define the image img dot property, all of property names I simply copy and apply. So now this is my function. This function simply compute with my this variable, because here I compute NDVI and LST, this variable. So now we find out that for every image we compute the relative soil moisture index SM, and it's indicating the distance from the edge. Okay, and also we also find out all of those in here. And this value will be 0 to 1. Okay, this value range will be 0 to 1. Okay, this is the range about that. So basically fractional position. Okay, suppose 0 indicating about that 0. Okay, suppose 0 or near to the 0, or high positive value indicating about that soil moisture is very high. Okay, we find out the fractional position, fractional, suppose 0 0.1, 0 0.3, so it increasing. Okay, high positive value indicating about the high soil moisture content, and low positive value it's indicating about the low soil moisture. Okay, we can easily find out this range between the 0 and 1. So now further, if you want, you can also make the time series chart of the soil moisture and display the soil moisture, as well as you can also show the soil moisture layer. Okay, so let's we try to create the time series chart and check what happened for this. For the time series chart, just simply take a variable, suppose chart, and call UI dot chart dot image dot series. Okay, so in this case we find out suppose first argument is the image collection. I already make the image collection. Okay, you can check this is my image collection SM. Just I copy and paste here, and then call the RY shapefile variable name, and I do compute EE dot reducer dot mean or average soil moisture compute. Resolution I put the 30 meter for Landsat, and apply is a system time start. System time start. So now I just print the chart and check the result of soil moisture. Now we face a problem. It show the expression contains undeclared variable SW. Oh, sorry. We need to define SW. We already computed. So run the code again. Yeah. What are we find regency? We find out this type of soil moisture information. So when it will be high, you can see, you find out that this is the high. Okay, you can see, and you can find out the very low. You can see this time very low. Negative is the very low. Okay, so this is the soil moisture time series chart for this time. We find out.
So it is possible to have negative values.
So negative will also find out, no problem. Suppose less than negative indicating about the more driest place. Okay, more driest, not much the soil range. Soil moisture is very low for this type of place. Okay, so you find out this type of map. You can see when it will be high. This is the high. Okay, then you can see decrease, and also find out in here you can see. Okay. And further, if you want, you can also display this map for your study area. Okay, so another thing is that in this, if you want, you can also just simply, suppose in this area we have some water body. Okay, you can see this type of water body. So if you want, you can simply remove or max all of water body, okay, or all of water or build up area. Suppose I just simply max, keep everything except water, build up area, or bare ground. Okay. So further, if you want, you can also use here the land use land cover map also. Suppose you have a land use land cover map for the study area. So further, we can also remove all of suppose water, then build up area or others. Then we also find out the more better map for the soil moisture. So now in this place have the some water body. So if you just simply remove the water body, okay, then this type of place it's not affected in your formula. Otherwise it also affected. So this is another thing is that, and when you work with only for the cropland, suppose in this time I take the big area, so that's why it also including others water body other thing. But when you work with the only for the cropland area, then just take only for the study area for your cropland, okay, only for the land of agricultural land, okay. But in this time I just take the other feature also. So now this type of other feature, suppose water body or barrel or build up area, this type of things I simply remove, okay, and make the map. So how I can remove the one thing is that you can easily make the land use land cover map, and you can easily remove all of those. Or if you want, you can also use some dynamic data. Dynamic data basically you can also apply some you can also apply some ready-made data. Ready-made data basically, suppose one data set, I will show you that it's a dynamic land cover data. Suppose I simply say starts here dynamic dynamic yeah, so this one. So from this data I just simply remove some water, you can say water I simply remove, okay, as well as the build up, okay, I just the build up I just simply remove, okay. Then we can easily make the better map for exclude water and build up, okay. So when you remove then you can find out the more better map. So let's go try to use it. But when you apply it for the agricultural land, then just take only for the agriculture area, only for the barren land area, so it will be more better. But in this case my study area have some build up area or some water body area, so that's why I simply apply this technique to remove all of others pixel from water body and also from build up. Otherwise it also mix, sometime barren land is also mixed with build up, okay, we already know about that. So just I copy. So I take a variable, suppose I put the variable is the LULC, and then call paste here, okay, and I select the band name. If you check this data set have the band name is this band name is level. I just take copy. Level and put here dot filter bounds with my study area which is ROI, and then also put here I apply suppose mode, okay, I take the mode, and then okay, just take another variable, suppose max, and just I
So
max
mode means
mode, okay, median mean mode.
yes. Okay.
Yeah, median mean mode. This is another statistical function. We take the mode values for each land use land cover, and I take the max and I just call the LULC dot, I put equal, I choose the class 0. 0 is for water, okay, 0, and also or I take the another, suppose LULC, I set equal 6 is for build up, and finally I put here dot not function. So when I put the dot not function, then it will be not max with my land use land cover map, okay. Basically 0 and 6 I just simply remove 0 and 6 using the not function. So now we just take the map dot add layer and call the max and clip with our study area, which is ry. And then if you want to go, I put the, okay, so now run the code and check what happened. So in this case, it display the land use land cover without water body and build up, because I simply max out. So again, so we find out this type of result. Okay, so now we find out. So now it's just remove this type of color, basically black color. It's indicating about the water body or build up. So this type of place simply max out. Okay, so now we simply check the soil moisture only for this white color region. So let's go. So for that, stack sm soil moisture image into a single multi-band image, apply the max. So take a variable, suppose sm maxed, and then call this sm. Okay, and then dot, I put here the two bands. So when we apply the two bands, then what happened? Then it show display all of image results. Suppose I have total 6 images, so it show the total 6 image result. Okay, for the first image, second image, third image, all of those display. And I want to display it only for this white color. So for that, I simply remove all of 0 and 6 and keep only for this type of class. So for that, just apply the update max. So this condition I want to apply. So this max, just I copy and paste here. Okay, so now these two bands, it mainly show the all of images, total 6 image result I find out in here, and I want to need the result only for this without 0 and 6 basically water body and build up, without water body and build up. So just put the update max and put this condition in here. Okay. So now further we try to display the result. So map dot add layer and call the sm maxed and run the code. So now it added the soil moisture without water and build up. Okay, so okay, we need to run the clip also. Just a minute. I think, yeah, two bands, then put here the dot clip. We can also put here suppose dot clip with RY. So now you can see the map. We find out. So you can see this type of place have the water body, or this type of the build up. So that's why you can see it not adding. So we find out only for this. So now add the color. Suppose you can see we can get all of those. So I want to display, you can see the first image, second image, third image, well, 6 images. Or if you want, you can just simply compose it all of image. Suppose average result you want to check, you can also do it. So for that, simply use here the dot mean function, and then it show the average for all of place. So I want to display it, and it's just 98% I keep. And further add the color plated. Suppose I put here that this type of red color for low soil moisture, then this type of yellow color, then this type of green color, And high soil moisture, I will show this type of. So if now we find out this type of map, so from this map we can easily get this type of blue color. It is the high soil moisture content. This type of red color is the low soil moisture content, and you already remove the water body and build up from our map. So now this is the final map of soil moisture. Okay. So you also try using the Sentinel-2. Same process, just apply using Sentinel-2. Okay. I hope you can easily get it because same approach, same band, same, all of those are the same. Okay, just we need to change the band name for the Sentinel-2. Otherwise, all of those is the same. Okay. So now you find out the soil moisture. This is the soil moisture map. Okay, we can easily identify, and this is the time series chart about that for the soil moisture. So this same code you also try to use and develop this code using Sentinel-2 satellite imagery. Okay.
Sir, but in Sentinel-2,
Yeah.
there is no thermal band.
So we find out the SWIR band. Okay, short wave infrared one. And for the thermal band, what we can do? Yeah. So this is a good question. So for that, what can we do? Because SWIR don't have the thermal band or LST band. Okay, so
Yes.
for that, I think we need to apply the another approach. We need to compute another way, I think, because for that there is no data.
And here we, in Yellowstone, we have used the band number 10, which is the thermal band.
Okay, so
We
for
didn't use
that we need to apply the STR. Okay, STR. Okay, so let me show you that what is the STR. So we need to change only for in here, because there is no thermal band, so we need to change in here. So we simply replace using the STR. Okay, so it's called the STR basically it's one kind of formula. This STR have a formula. I'll show you that just a minute. So STR formula. In remote sensing. Okay, STR. What is the STR? Yeah. So STR equal to 1 minus, this is the formula about the STR. STR. Yeah, STR. So now we need to apply the STR. Okay, otherwise all of this is the similar. But we need to apply the STR, and STR SWIR transform the reflectance, and it's called the STR. Okay, so SWIR band is available in the Sentinel-2. So this SWIR band transform the reflectance, and it called the STR. STR have a formula. I will show you that formula. STR formula. STR. And in this paper, basically, they also discuss about that. Basically, how we can easily compute the soil moisture using the Sentinel-2 use of STR band. Okay, but Landsat is the available for the surface reflectance. Okay, and its Landsat is called the OPTRAM 1. Okay, this is the previous model OPTRAM 1, but OPTRAM 2. Okay, this is the newest model. Okay, newest model. They also add here the STR and also compute. Okay, their Bollard engine, they also use was improve the satellite processing alloys. Okay, and also OPTRAM input STR. Okay. SWR transfer represented as STR. Okay, STR. Okay, so this is the formula about the STR. 1 minus SWIR divided by 2 multiply SWIR. So this is the formula. Okay, STR formula. This is the STR formula. Okay, 1 minus SWIR, you can see OL squared divided by 2. So this is the STR formula. So this STR formula we simply apply in here. Suppose I'll show the just to show you the one comment. Suppose I want to compute the STR. So how I can compute for Sentinel-2? So STR we simply change in here without instead of the LST. Simply take a variable. Suppose STR equal, I call the element name IMG, then apply the expression. Suppose my expression is that I compute the equation. Okay, I compute the equation is 1 minus SWIR, then power 2. Power 2, basically this 2 multiplication, it's called the power 2. And then after that, we close the bracket. Okay. Then divided by, we put here 2 multiply SWIR. So this is the formula. Okay, so this is the formula. So in this case, when we apply the Sentinel-2 satellite imagery, instead of the LST, we just apply this formula. Okay, for then other are all of them are the same. So now we simply define, just put the comma sign and put the define what is the SWIR. Okay, so simply define SWIR. It's come from your image and select the band of B12. Further, simply put the dot rename and put the name, suppose STR. Okay, so now these things we simply add. These things simply we need to add when we apply the Sentinel-2. Others are the same. Okay, so instead of this line, just put this line. Okay, in the Sentinel-2, and others, as well as we need to multiply the scale value of the Sentinel-2. Okay, and also select the Sentinel-2 band name. Okay, you also try. Okay, because this is the LST. Okay, for that Sentinel-2 we are just apply the STR and compute. So just apply this formula, and then we compute the STR and then make the soil moisture. So you also try develop this type of code. Same process, just only add, and others are the simply same. Understand the band name, others is the same. Okay, so you can do the no problem. So now we talk about that another important crop water stress index. Okay, so let's go. So I hope you also get the idea about the soil moisture for the Landsat and Sentinel-2. Then you can apply. Okay, no problem. Crop water stress. Okay. Okay, so now we talk about that crop water stress, how we can easily monitor. So let's